Okay. In this video, let's talk about section 3, completeness axiom. Okay. So let's see the definition. First, let E be a subset of R, non-empty. Okay. Then we have several names, notation. The set E is said to be bounded above if and only if there is a capital M in R such that A is less than or equal to capital M for all A in E. So if there's a roof, we say it is bounded above. Okay? And this M is called the upper bound. Okay, so a number is a duplicate definition, but let's just list them. A number M is called an upper bound of this set E if and only if A is less than or equal to capital M for all A in E. It's the same notation. For the same condition, E is called bounded above, M is called upper bound. So that's why I say it's a duplicate there. Okay, so of course you can get the counterpart, what is bounded below and the lower bound. Okay, so you can write down the definition on your own. And after the bounded above and the upper bound, a number S is called a supremum of the set E if and only if S is an upper bound of E and S is less than or equal to M for all upper bounds M of E. So when you have the minimum, the smallest upper bound is called a supremum. Okay, the smallest upper bound. The smallest upper bound is a supremum. It's upper bound, but it's the smallest one. Okay, and we write this as a sup of E. The sup of E. Okay. So in this concept, especially the third one, when you want to determine a supremum, you need to determine two cases. One, it is an upper bound. Second, it's the smallest one. All right. Okay, let's see the example. See how do we find some upper bound. So if E is a closed set 0, 1, prove that the supremum of E is equal to 1. The supremum of E is equal to 1. Okay, so we're going to show it is upper bound, it's the smallest one. By the definition of interval, what is the definition of interval? Definition of interval means 0, 1 is a set of all x such that x is between 0 and 1. So by this definition, we know that every element from this set is less than 1. So 1 is an upper bound. Of E. See, we actually showed half of a problem. From the definition of interval, you automatically get E1 is a upper bound. And then next, you're going to show it is a minimum upper bound. Minimum upper bound, smallest upper bound. Let's select arbitrary upper bound. So let M be any upper bound of E. Upper bound of E. So x is going to be less than or equal to M for all x in E. That's the definition of a upper bound, right? So x can be any number. So here 1 belongs to E. 1 is one of them. So it follows that 1 is less than or equal to M for any upper bound of E. All right? Yeah. So from the definition of upper bound, we can see that 1 is less than or equal to M. So 1 is upper bound, and 1 satisfies this condition. So by the definition of a supremum, one is the supremum of E. Right? So whenever you want to show it is a supremum, you have to prove two results. One, it is upper bound. Second, it's the smallest upper bound. Okay, the least upper bound. This is the example. All right? And a set has an upper bound. It can have infinitely upper bound. Why? If a set has one upper bound, it has infinitely many upper bounds. Well, it's obvious. If you stand in your house, then the roof is above you. Any higher roof, the roof above your roof will be higher than you, right? Any number greater than upper bound will be upper bound. So the proof is trivial. So if M0 is an upper bound, for any M greater than M0, M is an upper bound. It's a transitivity of the inequality, right? Any bigger number will be automatically an upper bound. So upper bound is never unique. Upper bound is never unique. But the supremum is unique. So we're interested in unique elements. The infinitely many elements is not that interesting. So if a set has a supremum, then it has only one supremum. If it has one, it will have just one. Okay, that is the uniqueness. How do we get the uniqueness? I mean, of course, if after we prove this is unique, then we can say the supremum. We don't have to say a supremum, right? The supremum. Why it is unique? We prove it. We prove this by showing if you have two, they are equal. Assume that S1, S2 are supremum of E. So you have two supremums of E. S1 is an upper bound. Any supremum is an upper bound. Then S2 is less than or equal to S1. Why? S2 is supremum. Supremum is the smallest upper bound. So supremum is less than or equal to an upper bound. Arbitrary upper bound. Supremum is less than or equal to arbitrary upper bound. Similarly, S2 is an upper bound. S2 is a supremum, of course it is upper bound. Then S1 is less than or equal to S2 because S1 is also a supremum. It is less than or equal to arbitrary upper bound. So this is like tautological stuff. Once you prove S2 is less than or equal to S1, S1 is less than or equal to S2, then S1 is equal to S2. So there is only one, the supremum. Is unique. See? So sometimes when we show two things are equal, we always prove one number is less than the other, less than or equal to the other one, and the other one is less than or equal to the first one. Then they have to be the equal. Right? This is the definition of supremum and the simple property. And the next theorem, we're going to give an equivalent statement about the suprema by the approximation. Approximation property for suprema. Approximation property for suprema. Okay, so what is approximation property? If E has a supremum and epsilon is greater than 0, is a positive number, okay, then there is a point A in E such that A is less than or equal to the supremum and is greater than the supremum minus epsilon. So it can be very close. How close? You can decide. You choose this epsilon as a small gap, then we can find a point close enough to the supremum. Okay, so that's a so-called approximation. Actually, this is also the equivalent result. If you can find some number like this with this property, then this number is definitely a supremum. Okay, if you have a number capital M such that for every epsilon, you can always find the A between M minus epsilon and M, then this M is a supremum. But we don't show that equivalence. We just show this one. Supremum has this property, approximation property. Proof. Suppose that the theorem is false. So we show by contradiction. A theorem is false. How do we get the corresponding statement? Okay, so now let's practice to find the corresponding statement for the negative statement. Okay, so let me rewrite this theorem. Let me rewrite the theorem, and then we see how do we write the corresponding negative statement. The theorem is the following. E has a supremum, so let's leave this. Epsilon is a positive number, so here epsilon is arbitrary. So for arbitrary epsilon greater than 0, there is a point A. There is a point A between E, inside E, such that the supremum minus epsilon is less than A, less than or equal to the supremum. Okay, so basically that's the idea, the meaning of this theorem. Now, if we claim this theorem is false, so the false statement means whenever you see for all, you change it to be there exist. Whenever there is a exist, you change it to be for all. Okay, so what is that? It says for there exists epsilon greater than 0. There exists epsilon greater than 0, such that for all A in E, for all A in E, such that A does not lie in those two numbers, lie between those two numbers. A does not lie between supremum minus epsilon 0 and supremum of E. And this number, let's call it S0. That's the number, let's call it S0. Okay, so that's the way to write the negative statement. You change for all to there exist, you change it there exist to for all. And of course, you get the negative statement of this conclusion. Okay, A does not lie between those two numbers. A automatically is less than supremum. This is always correct because supremum is upper bound. So A is always less than or equal to the supremum. This always holds. Then what this mean? A does not lie between them. This means that A is less than or equal to the supremum of E minus epsilon 0 for all A in E. Okay. Again, this one in the textbook is denoted by S0. This expression is called S0. So S0 is an upper bound. Of E. Right? Every element is less than or equal to this S0, so of course it's upper bound by the definition. And upper bound, supremum. For supremum, we have the supremum of E is less than or equal to upper bound, arbitrary upper bound, and supremum of E minus epsilon. From here, if we cancel supremum of E and move epsilon to the other side, we get epsilon is less than or equal to 0, right? You cancel a supremum of E and you move epsilon to the left side, you get epsilon is less than or equal to 0. But we assume epsilon sub 0 is greater than 0. You see, that's a contradiction. That is a direct contradiction. A direct contradiction. We assume a positive number, and then finally you get a negative number. And this contradiction comes from your assumption. You suppose the theorem is false. So theorem is true. The theorem has to be true. Okay? So you have a supremum and you subtract supremum by a tiny positive number, then definitely this is not an upper bound. Some element from the set will be greater than it. Okay, so that's an approximation. A is very, very, very close to the supremum. Okay? So again, supremum is an upper bound, but supremum may not belong to the set. This is not always true. The supremum of the set may not belong to the set. Sometimes it belongs to the set, sometimes it does not. There is no direct readout so far. So far we don't have the readout. And in some special case, we can claim it. We can give a readout. But in general, so far we don't. If E is a subset of natural numbers, E has a supremum, then the supremum of E belongs to E. The supremum of E belongs to E. Okay? So for the subset of natural numbers, once it has a supremum, the supremum is an element of itself. Okay, so that's a special property for the natural numbers. A special property for the natural numbers. So let's see the proof. Actually, it is also a same property for the integers. Integer also has this property. You will see you can modify this theorem a little bit and then apply it to the integers. Okay, so let's try to show it. It has a supremum, so suppose S is the supremum of E. S is a supremum of E. And the approximation property, what is approximation property? By the approximation, by the approximation property for epsilon equal to 1, there is an x0 in E such that s minus 1 less than x0 less than or equal to s. Right? It can be the supremum, but it is strictly greater than the supremum minus epsilon. Okay? Well, let's see. If the case 1, if this x0 is equal to the supremum, x0 is in S, the theorem is done. Right? So if it is if it happens to be x0, then nothing you need to prove. You just want to show the supremum belongs to the E. Here, supremum is x0. x0 belongs to E, so supremum belongs to E. If this is the best case, then there's nothing we need to prove. Otherwise, the case 2. For case 2, we have strict inequality. Strict inequality. So x0 is strictly between s minus 1 and s. Okay, then apply the approximation property. Approximation property. What is approximation property? For what? Basically, approximation property means you have a supremum, you choose an epsilon. So what is an epsilon? The essential thing for the approximation property is that here is the supremum, here is the supremum minus epsilon. This supremum is fixed, but supremum minus epsilon is moving. This moment, we have s as a supremum here. x0 can place the role as a supremum minus epsilon, right? So first you get s here. Here you get s minus 1. x0 is not equal to s, so x0 is here. Well, remember x0 is an integer. x0 is an integer. So you can consider this little gap. x0 is between this bigger gap. Now you consider this little gap. Okay? In between this little gap, there is a x1. So that's what we say apply the approximation property. For what epsilon? Here's s minus 1. This distance is a 1. Here, epsilon is going to be s minus x0. Epsilon is s minus x0. Then what we get? S minus epsilon. You see, s minus epsilon is s minus x0 is x0. So the s minus epsilon becomes x0. For epsilon, there is an x1 in E such that x1 is between s minus epsilon and s less than or equal to. And here this is positive because we assume it is strictly less than s. Okay, and let's rewrite this. This is x0 less than x1 less than or equal to s. x0 less than x1 less than or equal to s. All right, and then next, let's see if x1 is equal to s, then it's done, right? x1 is equal to s. Now the theorem is done. If not, x1 is strictly less than s. x1 is strictly less than s. Then what we get? We get, let's see, several things we can get. We get 0 greater than x1, 0 less than x1 minus x0, and less than s minus x0. So this distance. Okay? If not, we have x strictly less than it. And that's why you get the strict inequality. Strict inequality. And x1 is greater than, not x1, x0. x0 is greater than s minus 1. So it's less than s minus 1. It is equal to 1. right? So the distance between x0 and x1 should be less than this 1. Distance between s and s minus 1. And we also know that for two integers, different integers, x1 is greater than x0, the difference is greater than or equal to 1. But here you get the difference is less than 1. That's a contradiction. Here when I say the contradiction, I do not say this is a wrong statement. Here, this one is impossible. Okay, the contradiction comes from here. This one is impossible. You cannot find a pair of integers such that they're different. A pair of different integers such that the difference is less than 1. This is correct. This one is incorrect. This incorrect result comes from your assumption. x0 is not equal to s. The first case is okay. The second case cannot happen. Okay, so combine those two cases. The supremum of E belong to the set of E. Belong to the set of E. Okay, so you can see that in this whole proof, you use this property. Your contradiction is based on this property. This property holds for the set of natural numbers. It also holds for the set of integers. But this property does not hold for the set of rational numbers, irrational numbers, and real numbers. So that's why I say this proof, this whole proof, it can also be applied to the subset of integers. Okay, it can also be applied because it contains the same property. If you do not have this property, of course, you cannot copy this proof. Okay, so that's a supremum argument. Now let's see. Postulate for completeness. Completeness axiom. Completeness axiom. If E is a subset, non-empty subset of R that is bounded above. Okay, non-empty subset bounded above, then E has a finite supremum. Why do we need this one? The thing is that if you change this R to be Q, the set of rational numbers, this property does not hold. This is a special property for the set of real numbers. And this is considered as an axiom for the set of real numbers. It's completed. Okay? The thing is that, okay, for example, remember that the pi, for example, let's talk about the pi. Pi it's like 3.1415926 blah 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 stuff. It does not stop. And then we can use the truncation property to get approximation. So 3.14, 3.141, 3.1415, 3.14159. So you collect all those numbers together. You collect all these numbers together to form a set E. To form a set E. It's an infinite set. It's an infinite set. And all those numbers are finite decimal numbers, so they are rational. So this E belongs to the set of rational numbers. And pi is an upper bound. Once pi is the upper bound, pi is the 3.14, right? And any number greater than pi will be upper bound. For example, 4 is also an upper bound. But pi actually is the supremum, the smallest upper bound. If we only consider this subset E inside the Q, not inside R, pi is irrational, it's not inside the Q. So if we only consider E in Q, then E has upper bounds. This is upper bound. E has upper bound, but E has no supremum because pi is missing in the rational set, in the set of rational numbers. Pi is missing. There is a hole there. Okay, so that's for some reason we say Q is not complete. There's always hole. There's a lot of hole there. But for the R, we get this completeness axiom. We believe R has no holes because we use irrational number to fill the holes. For E in R, the supremum of E is equal to pi by completeness axiom. Okay, so after we add the irrational numbers, there is no hole for the real numbers. Okay, so that's one of the property. Okay, so this is a very abstract property. Now let's see some applications. The application, the statement is trivial, but you need to focus on the proof. How do we go step by step? Solo from the framework we just built up to get the result. If you do not start from the framework, just from your common sense, you don't have to prove any of the theorem because they are so trivial. But we want to just start from our framework, the basic skeleton. We want to get the whole picture. Okay, so the theorem is Archimedean principle. Archimedean principle. Let's see what is Archimedean principle. So given positive real numbers, A and B, there is an integer n from the natural numbers such that B is less than n times A. See, it's so trivial. You may say, okay, let's just pick up n as large as possible, so even definitely this is correct. But how do you convince me definitely? That word is not very clear. It's a subtle word, definitely, eventually. Okay. Okay, now let's see the proof. Basically, the proof, the idea is trivial. So what is the idea? The idea is that you are going to set, okay, we want to build a non-empty set of integers. Okay. We want to build a non-empty set of integers with what property? Such that it is bounded above and with the largest integer. Okay, so the subset of integer with largest integer. Why? Because we do the following. See, we want this happen. So Ka is less than or equal to b. Ka is less than or equal to b. So here you want n times a greater than b. N times a greater than b. Then let's just find its opposite. You get all the k such that Ka is less than b. Then for this one, if E has an upper bound, if this set E has an upper bound, then it will have a supermem. Right? It have upper bound, it has supermem. You have a supermem, add 1. Then k plus 1 is not in E. K0 plus 1 is not in E, so K0 plus 1 times A is not less than B, it's greater than B. And that's it. Right? So in the process, it seems like where do we use this the completeness axiom? The usage of completeness axiom is that the supermem, the existence of supermem. So here you only assume it has upper bound. You only assume it has upper bound. From upper bound to supermem, you need this completeness axiom. All right, and also you have to notice why this is a non-empty set. Completeness axiom is applied to non-empty set. Where did here? Non-empty set. All right, so there are 2 questions you need to answer. So that is the idea. We build up this set, and we verify those 2 conditions. Once we verify the condition, we can get the conclusion. Okay, so let's see the cases. You have positive numbers a and b. This is idea, not proof. If b is less than a, choose n equal to 1. You are done. If b is less than a, choose n equal to 1. There's nothing you need to do. If a is less than or equal to b, then we define this set. Let E be the set K in the natural numbers such that ka is less than or equal to b. Okay. When k is 1, a times a is less than or equal to b. So 1 belongs to E. E is non-empty. So see, the non-empty, this property also comes from one case. Okay, comes from one case. Okay, so k times a less than or equal to b. A is a positive real number. Where is a positive? Yeah. A is a positive real number. We divide this inequality by a positive number. We get k is less than or equal to b over a. K is less than or equal to b over a. And this property holds for all k in E. Right? This property holds for all k in E. So what? E is bounded above. E is bounded up above. Non-empty, bounded above. Okay? If you want, you can say this is upper bound. One of upper bound, but it doesn't matter. Okay, then by completeness axiom, postulate 4, by completeness axiom, E has a supermom S that also belongs to E. Okay, now let's see. Completeness axiom say has a supermom. Belongs to E. This result comes from the let me say. Comes from the remark 1.21. If you have a subset E in the natural numbers with a supermom, then supermom belongs to E. Okay, so completeness only provides the existence of S. It does not contribute for this belongings. Okay, now let n be S plus 1. N is S plus 1. N is a natural number, and N does not belong to E. Why N does not belong to E? Because N is greater than S, the supermom. N should be less than the supermom if it is belong to E. But here N is strictly greater than the supermom, so N does not belong to E. N does not belong to E. N does not satisfy this condition. So B is less than NA. That is what we want. Right? So this is an Archimedean principle. This is Archimedean principle. The proof is not difficult, but you need to understand why, or what steps, or what rhythm behind the steps. Okay? So you need to know the rhythm behind the steps. And now let's see the examples. We will have two short examples finish this video. Okay, so let A be a subset 1, half, quarter, 1 over 8, and B half, 3/4, 7 over 8. Okay, prove that the supermom of A is equal to the supermom of B is equal to 1. So first, 1 is a supremum, sorry, an upper bound for A and B, because 1 is greater than or equal to any of the element. So this is clear. And we need to show that 1 is the smallest. Upper bound. 1 is the smallest upper bound. For A is trivial. It is trivial because A contains 1. A contains 1 if you have element. You have upper bound. It's like the closed interval 0, 1. If you have an upper bound, then 1 is less than the upper bound. So for set A is trivial. Actually, in this example, we also have a result. If an upper bound belongs to the set, upper bound of the set belongs to the set, then it is the supremum. Okay, so that's exactly the situation. Okay, so you can imagine how do you show it. If you don't know how to show it, check the example 0, 1 has a supremum 1. Okay, now let's focus on B. So let M be an upper bound for B, for the set B. And M is greater than 1. M is greater than 1. Okay, I'm sorry, M is less than 1. So if M is not so this means 1 is not the smallest upper bound, so 1 is not the supremum. So basically we again show it by contradiction. Okay, so remember that if you have another upper bound less than M, less than 1, so 1 is not, here we assume 1 is not the smallest. The same thing, 1 is not the smallest. Okay, so M is less than 1, so 1 minus M is greater than 0, and 1 over 1 minus M is also greater than 0. Okay, then we can find by Archimedean principle. By Archimedean principle, how do we do that? We compare for 1 over 1 minus M and 1. There is an n in the natural numbers. They are both positive, such that 1 over 1 minus n, M is less than n. Right? A is 1. B is this quantity. A is 1, B is this quantity. And if you do the exercise, remember, do the exercise, we have the conclusion n is always less than 2 to n. N is less than 2 to n. So it follows that 1 minus 1 over 2 to n is greater than M. So how do we do that? You just put just here 1 over 1 minus M is less than n less than 2 to n, and you solve for M, you will get this inequality. And this is a very important property, and we just use it in this place. It's not just a special property used in this place. It's just a special application in this place. Okay. Okay. Why we care about this? Because of this writing. This is 1 minus a half, 1 minus a quarter, 1 minus 1 over 8. That's exactly 1 minus 2 to n. That's exactly 1 minus 2 to n. So you get this. So what? You find a point. So M is not an upper bound. Upper bound should be greater than or equal to any element like this, but here you find one greater than M, so M is not the upper bound. It is contradiction. Where's upper bound? Contradiction. Right? This contradiction comes from your assumption M is less than 1, because M is less than 1, this is greater than 0, this is a positive number. For positive numbers, you can construct these steps. Right? So whole thing comes from this assumption. So this assumption is wrong. So M is always greater than or equal to 1, and 1 is the smallest. 1 is the supremum. 1 is the smallest upper bound, so 1 is the supremum. So that's the complete proof. Okay? So we don't have enough time, more time to discuss this Archimedean principle. We will continue in the next video to discuss this application of Archimedean principle. Okay, we'll stop this video and continue in the next one.